So let's get started with our afternoon session, which is also the last session of this entire workshop. So I hope you've had a great few days. But the speakers here are maybe the last, but they're certainly not the least. And we will begin our afternoon session with Wynn, Jacobson, Galan, a NSF graduate fellow at UC Berkeley, working with Professor Raffaella Margutti, who will be telling us all about the detection of pre-supernova activity and what we could do with LSST for that. Wynn, take it away.
Cool, thank you. Yeah, this has been a really great conference. It's made me more and more excited for Ruben and LSST. And yeah, so I'm Wynn. I'm a graduate student at UC Berkeley. And primarily I work on mass loss and red supergiants moments before explosion. And I wanted to kind of touch base on, talk about that, and also frame it in the context of LSST, because I think it's an exciting time to be looking at the final stages of stellar instability and mass loss for massive stars. Before I begin, I'd like to make a land acknowledgement. So I'm situated in the UC Berkeley campus that is a part of the Ohlone people, and they're an active part of our community. Same with Keck observations and basically utilizing the space of those people for our scientific benefit. And I think it's important that we acknowledge it and then bring them into our community and participate. All right, so I wanted to kind of give an overview of what I'm going to talk about. So part one of my talk is going to be very specific to one supernova, and then I'm going to kind of push that towards LSST and frame it in the context of what can we learn about supernovae after they go off, and what can we learn about the progenitor stars by looking at them before supernovae occur, and how can LSST basically push us into a new frontier of this. You probably already heard a lot about the Young Supernova Experiment. We've kind of dominated this conference already, but you should know that it's an amazing time domain survey using the Pan-STARRS 1 and 2 telescopes. And I just want to highlight the depth here. So 21.5 mag is technically the most optimistic limiting magnitude that we can get down to with the survey. And it is the reason why I have such exciting science results to share with you. It's because unlike other surveys, it uses multiband filters, but it also pushes down to deeper magnitudes. So I wanted to kind of frame this talk in something that I'm interested in, this nice talk that I like by Chris Kachanik. So basically what we don't know about massive stars before they die is kind of highlighted in this talk, and it highlighted in this plot. So on the x-axis, we have progenitor mass, and then y-axis, we have time before explosion. And these are the supernovae that we've observed, and then the relative progenitor star masses that we've inferred from pre-explosion observations. So we saw the supernova, we went back, we checked, and we saw the massive star companion for this supernova, and then this is the time scales that we saw it. So as you'll see, there's definitely a lot of this phase space that's unexplored. And we really don't understand what massive stars are doing before they die, because we just haven't observed enough of them like moments before explosion, because we don't know where they are. We're just kind of looking all around the sky, and then we see a supernova, and we're lucky if we have HST imaging that could tell us, okay, this was the type of star that went off before explosion. But what's really cool physically is that each stage leading up to explosion corresponds to what the star is doing in its interior. Is it burning carbon? Is it burning oxygen? Is it burning silicon? Those are final evolutionary stages that are crucial to why stars lose mass, why stars die the way they do as supernovae. And we should be able to fill this plot out. So I want to kind of emphasize that this plot is kind of the driving force about what I'm interested in and what I think LSST and the observations that I'll share about EZ has done and will continue to do, which is super exciting. So the first part of my talk is about a specific supernova before I get into the general physics. Just to kind of go through the specifics, supernova 2020 TLF was a Yeezy observed type 2 supernova. It went off in a nearby galaxy at 37 odd megaparsecs, so pretty nearby. And we were really excited about it because Yeezy was a new survey and we had detected it early on, and it was a young supernova that we had observed. So we got a nice Keck spectrum. And I will go into the specifics of the spectrum, but what you'll notice is it's pretty much just a hot blue continuum. So something really hot has gone off, and then there's these kind of weird looking narrow lines on top of it. So what is this supernova? I'll get into that in a second. At first, maybe we were thinking it's some sort of type 2N. There's clearly some CSM or circumstellar material sitting around the star because we see these narrow lines, but we have no idea anything more. So we got interested in it. We followed it for longer, and it became sun constrained. So all we had was basically photometry from space. So Swift Space Telescope filled out our light curve. And even though we saw that these narrow lines were there, it was kind of a type 2N looking thing. It actually behaved more like a type 2, type 2P, type 2L. So a normal plateau phase supernova that then falls off on its radioactive decay tail. So that's odd. And I will get into the specifics a little bit more, but what I want to highlight is that Yeezy was observing this field and this supernova in particular well before the discovery magnitude, the first detection, and then, in negative phase space, so before explosion as well. So that's, a precursor to what I will talk about. The supernova thankfully came back from behind the sun. We were able to get an observation, and it kind of confirmed what we were thinking. This thing is not just a narrow line interacting supernovae. It's now transitioned into a normal type 2, type 2P, like we normally learn about and hear about as the most common supernova type. It's a red supergiant explosion that now has this really massive hydrogen envelope and that's recombining and producing these normal P Cygni lines. And so we continue to follow this out to nebular times, and it behaved pretty much normally. But it clearly had some weird stuff going on in its early spectrum. And what we usually call this is, quote, flash spectroscopy. So flash spectroscopy really just refers to getting on target rapidly or in a flash. But sometimes people try to link it to a physical thing, which is not always the best practice, because after shock breakout, the star will emit a shock breakout pulse or a flash of radiation. And whatever stuff or gas is sitting around the star at the time of explosion will suffer the consequences of that blast of radiation. And it will photoionize whatever gas is sitting around the red supergiant star. But if there is no continual ionizing source that continues to pump energy into that gas, those lines will recombine, and we would never see narrow lines around any, in any core collapse supernovae ever. So seeing narrow lines for a long period of time is because there's photoionization. There's a shock running through this dense stuff that's sitting around the star at the time of explosion, producing these narrow lines, which we've seen in quite a number of events. So that's already one piece of the puzzle for 22LF. It's a red supergiant star with a lot of stuff around it. That's why we see these cool narrow lines. And I mean, what's so amazing about these is that they are not derived from the supernova itself. They are derived from the wind and the stuff the star was doing right before explosion. So we are actually winding back the clock to see what the star was doing. And this material is stellar material, but it shed it while it was still physically a star, not a supernova. So moving on to what I think is the most fascinating part about 22LF is that, like I said, Yeezy was observing this field before explosion. So like HST, we wanted to do the similar thing and look back in time and see, is there any chance, that Yeezy could have observed something detectable from the progenitor star itself before supernova 2022LF. And so I nagged a lot of people in Yeezy, and I said, please, can we look into this? I really think there's something there. And yeah, it turned out to be pretty promising, because what you'll see here is this rising flux of pre-supernova emission. So this is the progenitor star. We're detecting luminosity from the progenitor of a star of a type 2 supernova for the first time. This is what it looks like in some sort of ejection scenario or something that's causing this enhanced radiation. And the way that we did this is we basically have some really deep template image. This is the image that we're trying to see if there's anything in, so the actual precursor image. Subtracting the two, you see this luminous source. And there's just more exposure in the I band, that's why it's brighter. But this is the first time we've ever seen this. We've seen precursors for normal interacting supernovae, but a normal-ish type 2 that comes from, we know, a red supergiant. To say we've seen the red supergiant doing some stuff before explosion, it's fascinating. This is like a whole new game changer. So this is really cool. We want to look for more. And I'll just go through what I think is now the next generation of what we can do with supernova science and progenitor science is make plots like this. So in supernova science, we usually start at time 0. That's when we think the star exploded. And then we make bolometric, black body temperature, black body radius plots from 0 onward. But now, because we can have detections of the star itself, we can transition from the star in bolometric space to the supernova in bolometric space for the first time. And LSST is going to be able to do this for many more events. And this is just the first time we've done it for a smaller ground-based survey. So we see the precursor, the star goes off, we see this plateau, and we fall on this radioactive decay tail. So all in one picture now for the first time. More about the star itself that exploded. I was saying it's red supergiant. It's probably of order 10 to 12 solar masses because the nebular spectrum compared to models can then tell us that. And we also wanted to understand the circumstellar material. So we modeled it with some NLT radiative transfer code. And we found that, yes, there was a pretty enhanced mass loss. There's a lot of CSM sitting around the star. And we were able to match the observations through this like synthetic spectrum and synthetic light curve models very well. So we now have a really nice picture of what this red supergiant was doing right before explosion and into the explosion itself. And so putting it all together, which I think should be our goal if we're trying to think about supernovae and the stars that produce them, is that there was a red supergiant. It was 10 to 12 solar masses. It was probably kind of inflated or puffed up, which makes sense for the mass loss that we think was undergoing. It was definitely struggling and having a time at the end of its life. It was losing mass at an enhanced rate, maybe more than a steady state Wynn could even produce. So something had to produce this. And we're seeing the luminous emission from this stuff. I mean, we're seeing it producing this in its final state. This is the precursor. This is the star doing this enhanced activity. So we're now putting it all together. And then the red supergiant star finally collapses and explodes. And we get to see the product, the 20 TLF, the supernova 20 TLF. And then as it interacts with its circumstellar material, we're able to understand what the star was made out of, how long it was losing mass, how extended is its circumstellar material, and then also, understand the progenitor star from supernova observation. So this is all one big picture. And I think it's really basically a stepping stone, and this should be like a prototype for what we should be able to do with LSST. And I wanted to put this in the context of this plot again. And now we're able actually to put our own data on this type of plot. And I'm sure there are other like supernova progenitors that we could add here too. But I want to continue to emphasize that in the second half of the talk that LSST will put more things on this plot. And this plot will now actually really help us understand the phase space of massive stars at the end of their lives. So moving toward the future, this is a plot that we made when we were making the paper on 20 TLF. And so you'll see the limiting magnitudes at 100 megaparsecs. 20 TLF is in the colored points here. These are precursors for type 2N, so interacting supernovae that remain in interaction in their circumstellar material for their whole life. So kind of different physically than normal type 2s. And you can see luminosity-wise, they're very different. LSST would have no problem finding these things. It's going to have no problem finding 20 TLF-like events out to 100 megaparsecs. So we're going to find, and unless 20 TLF and the red supergiant that made it is the weirdest thing ever, and I've just it's a one-trick thing, and I'll never have another event like this ever. That's really interesting too, because if LSST is on, it should see more of these things, and we can really understand the rates of which red supergiants are either super quiescent before they explode or super tumultuous before they explode. Knowing the binary, knowing what the difference is immensely powerful for stellar evolution. So I wanted to kind of go through what I've kind of collected in terms of what can power a precursor event and where are we at in terms of our community from the theoretical side, from the observational side. I've shown you the exciting promise of finding it observationally, but if we take it to the theoretical side, are we even in the right ballpark of understanding these things physically? Do we even understand what's happening inside the star? So I'll start with a couple mechanisms I've kind of compiled from the literature that I think will inform us when we start to think about observing these with LSST. So one is just agnostic. It's just you have a red supergiant, it has an extended envelope, it has some envelope, hydrogen-rich envelope, and you just have to inject energy into that envelope somewhere. Enough energy that it overcomes the binding energy of the envelope, a shock forms, and then the star just erupts material or loses material through a steady state wind. But this has no physical tie to what the star is doing. It's not linked to a nuclear burning phase. People just do this as a simulation truly at the surface of the red supergiant. So in 3D, this is a paper that came out 2 days ago from Benny Sang at UC Berkeley. And he's been doing these really amazing simulations, and the movies look really cool too. Hopefully he'll put those out, where you see this injection at some period of time before explosion. And then you see this really amazing plume of red supergiant outer, like exterior blowing off because the ejection of energy into this envelope succeeds in blowing off mass. And it's actually very like consistent with what we see for 20 TLF. And people do this for, simulations that actually try to predict the light curve and stuff. So these X's are actually 20 TLF. This is a paper by Nikolai Chagai, who looked at 20 TLF and made a similar model where he basically injected energy right there, and it produces the luminosity incredibly well. The similar thing has been done for type 2N precursors. So this is really promising. I am just worried that we continue to produce these observations, and yet synthetic observations, and yet we don't really know why the star would even have a burst of energy into its outer envelope. So we really need to think about if it's even possible to do this, and if these precursors, which work observationally, are really a physically grounded scenario. So something that is a little bit more physically grounded, but may not actually work for the red supergiant stars that I'm interested in, is these gravity waves. So this was proposed by Elliot Quater, Jim Fuller, and then his student Samantha Wu has really like taken on the charge of like seeing if this works for a wide range of hydrogen poor, hydrogen rich, like supernova progenitors. And so this is like the original 15 solar mass red supergiant, where you have a gravity wave that forms from some sort of burning, and that will carry the energy to the outer envelope. That will allow the like ejection of mass if there is any. And so this is the line from the synthetic model. These are observations from 20 TLF, and then 2N like precursors will be even higher in luminosity. So the problem is that it just doesn't produce enough luminous precursors. So it could work, but it's not producing the events that we've seen so far. But with LSST, we may be seeing these events and maybe confirming if gravity waves is a logical scenario or something that would actually work. So that's fascinating. This is for a hydrogen poor supernova progenitor, which we've never seen a precursor for. That would be amazing. So something that's already lost its hydrogen envelope and then it's doing more. Perfect. One thing that has been an interesting conversation is that they've only gone to stages of burning that are like in the last decade, so neon burning. To push into the silicon burning regime or instabilities there would be amazing, and gravity waves there could be really very interesting, but it's very complex, and theorists can't do everything, even though we really do think of them as gods, or at least I do. And so yeah, I think that's really promising. The last thing I will go off of is this enhanced Wynn scenario. So some sort of super Eddington rate of energy injection into the stellar surface, and then that blows off a lot of material. And so another paper by Matsumoto took 20 TLF in the red points you can see here and fit our precursor data with a similar model. It seems like a pretty enhanced mass loss rate, also agnostic to why there would be this energy injection to lead to something super Eddington. Maybe the stellar evolution theorists would be kind of concerned that this is not a physically grounded thing either. Is this really how stellar winds would work? We're not sure, but it's promising, and it will work to supplement and compare to LSST observations and new precursor events. So yeah, with that, I'll leave up my conclusions about 20 TLF. It's the first type 2 supernova with precursor activity, and with LSST, we should definitely find more, and that's exciting. But yeah, thank you.
Thank you. Sorry that I wasn't here for opening the session.
Oh, that's okay.
Thank you for the talk. Wynn. Questions? Yes.
Wonderful talk. My question was about the non-LTE modeling, which is how much is the mixing within a star considered when you do the non-LTE modeling? And I wonder if there has anything to do with the mass loss mechanism or the energy injection for that case, which we are trying to understand.
Yeah, that's a fantastic question. So these are specific to Luc Dessart and his CMF Gen and then Heracles models, where he starts with a supergiant, red supergiant, that he has to, like the models you showed, it's a simplified mixing length kind of theory that he uses. So he uses a mixing length parameter of 3. So it's definitely incorporated. It's a simplistic thing. Understanding the convection is like important, but I think that, yeah, I think that maybe it would be interesting to see like how the models you're using are comparing to his, and like I would need to actually like talk with him one-on-one to see. But yeah, I think it's still like a simplified, it's probably order of magnitude pretty similar between the models. Yeah, it's in there, but it's a similar, it's like simplistic mixing length theory. Yeah, for sure.
There is a question online from Costa. Costa, can you unmute and ask?
Thank you. Thank you for a wonderful talk. I found that probably this TLF precursor showed some variability back to the beginning of the ZTF series. So since the beginning of this ZTF series from 2017, and even maybe it shows variability in Pan-STARRS data release 2 back to 2013. So what could be the physical reason of this long-term variability? Yeah, so here you show only 100 days, and I'm talking about years.
Yeah. So we really focused on just what Yeezy had observed. So as you know, if it was non-detections for the length of Yeezy, so that went back to 2019, we only focused on that. And I do include ZTF data, but I did not feel comfortable reporting them in the same way that I did with Yeezy, because I was able to actually like put our hands on the Yeezy data, do the statistics like as well as we could with the precursor analysis. And I just didn't feel comfortable without actually having the ZTF data to do it ourselves. But yes, you're right. I mean, it did go back a long time. I didn't see it just in my initial pass. But yeah, I think that we could be more robust, and we're trying to be more robust with like a sample of these objects as well. So yeah, I think I'll let you know how that goes.
Yeah, so my main question, it was just, a comment. My main question about physical, what do you think about astrophysical source of these variabilities? So
yeah. Okay, I mean, yeah, I think maybe it could be the ejection of some sort of envelope, and maybe like internal shocks that are happening. So you have this initial ejection, maybe there's already CSM there, and then maybe that's powering like additional things as shocks form within CSM on CSM kind of impact. I'm just throwing out ideas, because also I don't think that these are strong enough detections to really confirm variability or not. I think we would need like a higher confidence detections. People have asked me about the variability in these data specifically, and I'm just like not sure what to say because I don't really believe it. And I think that if I said there was variability, other people would say no. So yeah, I think that I should like think more about that. But that's a really good point.
thank you.
Okay, so you talked us through the gravity waves, but while speculation time, we don't just have LSST, we also have LIGO. If these things are within 100 megaparsecs, sooner or later we're going to see gravitational waves from a collapse supernovae. What do you do when you have a really, really precise time of explosion, as well as this? What more can we talk about when we have a multi-messenger picture of collapse supernovae?
That would be amazing. I don't even know what I would do that without information. I would turn to Lindsay and ask what she would think. But yeah, I mean, a precise time of explosion is really important. I want, like, we don't even say time of explosion with red supergiants. We say time of first light. So when does the shock actually make its journey out of the star and then come out, like, out of the star? Is it breaking out of the stellar surface? Is it breaking out of the CSM? Yeah, to actually understand that, and then light travel times, unparalleled amount of information. That would be amazing. Yeah.
I'm gonna ask one more question myself. Oh, no, I'm not. Sorry.
Thanks. There's a really, really exciting results. I was wondering if maybe it's possible to do the same for type 1a supernovae, if you can see the progenitors and maybe distinguish between the different progenitor channels.
Yes. Yeah. So I mean, like, we should look. Like every transient survey should look. And I think that we are doing that for Yeezy. And I think that hopefully this is encouraging every other transient survey to try to develop their own method for looking. And we're going to look at type 1As ourselves. And I think, like, yeah, we should. I don't have any hope that we'll find anything, because, like, if there is some sort of precursor of a type 1A, it would be very low luminosity, right? Like, unless it's some sort of pretty violent thing, or CSM ejection or something. I don't think we could distinguish between progenitor channels, though. Maybe. I mean, unless people are simulating these already, and then they have things to kind of give us to confirm. And if there's some wildly dramatic scenario that's very luminous, we can maybe rule it out. Because I think what will be cool is that type 1As will push the limits very, very far down. So if there's no detection, we will really be able to say that there's no detection down to a very low luminosity. So yeah, I mean, that's fascinating. I think we should. Yeah, it's a great point.
I think we're very close by supernova type 1A there.
Yeah,
This is exactly how to set limits on the potential. Like
right. We've never seen
2011
one.
FP.
So yeah.
that's all the time that we have
Yeah.
for this talk. Thank
Cool.
you very much. And